Okay, chapter 14, solutions. There's a bunch of great reasons why you shouldn't drink seawater. One of them, it tastes really bad. The other one, probably the more important one, is that seawater is a thirsty solution, if we wanted to anthropomorphize it. It's a solution that as it goes through your body, as your body tries to process it, it's going to pull more water out of your body, and it'll leave you feeling more dehydrated, leave you being more dehydrated than before you drank the seawater. So it's actually a net loss. You'd be better off not drinking anything or finding a piece of cactus to suck on maybe. Seawater is a solution. What problem does it solve? Wrong kind of solution. It's a homogeneous mixture, which we can sort of think as smooth consistency, in case you've forgotten. An evenly mixed, single layer mixture of two or more substances. If it was just one thing, then it would be a pure substance. In this solution, water is our solvent. The solvent is the majority component. And in seawater, sodium chloride, table salt, is the primary solute. The solute is the minor component, or a minor component. Oftentimes, we'll also just talk about these as the solvent being the liquid and the solute being the solid, regardless of their proportions. But these are our technical definitions for solvent and solute. The majority component, the minority component. And there are other solutes in sodium chloride. In solutions, nature tends to mix. Spontaneous mixing. Spontaneous meaning it just happens. You don't need to put energy into it unless it's very unfavorable energetically. So if we start off with a little tub, we've got pure water on one side, we've got water and salt on the other side. This is sort of what would be happening in your body. This barrier would be cell membranes and stuff. If you get rid of that cell membrane, that barrier, then suddenly, over time, you'll get to this uniform concentration, even without mixing it up. It'll go a lot faster if you stir it, but it will eventually get to this uniform concentration. These sodiums and chlorides will work their way over among the pure H2O until you've got a uniform concentration, so that you pull from any part and it's the same concentration. So what happens when you drink seawater is that tendency towards mixing causes the solvent, the water, to drain out of your cells and into the seawater. They're pulled in by the intermolecular forces with those sodium chloride ions. It would go the other way, but your semi-permeable membranes stop the salt from moving through freely. So solutions, as I mentioned, oftentimes we'll talk about the solvent. The majority component will just mean liquid by solvent, and the solute will often mean solid. But you can make solutions of anything. Any two phases of matter you can combine to form a solution. So we can have a gaseous solution where one of our solutes is a gas and the other solvent, the other solutes even, are gases. So air is an example of a gaseous solution. There's a lot of nitrogen, there's oxygen, there's carbon dioxide, argon, some other gases. There's a bunch of liquid solutions you can have where our solvent is liquid. You can dissolve gas in liquid, like any carbonated beverage has CO2 dissolved in water. You can dissolve liquids in liquids. You can dissolve solids like salt in liquids, sugar as well. You can also have solid solutions, alloys, things like brass. Those are also technically solutions. Generally, when we're talking about solutions in chemistry class, we're usually talking about aqueous solutions. The aqueous is often implied, even if we talk about other solutions. Usually we mean aqueous solutions when we talk solutions. When you're making solutions, there's no universal solvent. So a particular solvent like water, hexane, etc., is not going to dissolve all possible solutes necessarily. So there are cases where not everything will dissolve. And our measure of how much will dissolve is solubility. This is how much solute will dissolve in an amount of solvent. I do occasionally rewrite things that are on the slides in basically the same words. I'll often just read them off. It slows me down, and then it also lets you know that it's important. So our solubility depends on how well things will mix and on the types of intermolecular forces. So there are certain matches of intermolecular forces that will lead to dissolution, solvation, and there's others that won't mix well. Do we have any questions so far? Lots of physical systems tend towards lower potential energy. If we form a solution, it doesn't necessarily lower the potential energy of the particles. An example of this is if we are mixing ideal gases. If we're mixing ideal gases, it doesn't lower their potential energy. So neon and argon here separated by a barrier, like we saw with our water and salt water. And if we remove that barrier, the gases will disperse themselves. They'll mix into a uniform solution. One of the ways that we can measure energy is with entropy. Entropy is a measure of two ways we can think of it: energy randomization, chaos, or energy dispersal, how separated, how spread out our energy is. When we have two ideal gases that mix, on the previous slide we saw they can't necessarily be thought of as lowering their potential energy. That's because of their entropy. When our two ideal gases mix, they're ideal gases, they don't interact with each other, there's no intermolecular forces. But we've spread out our kinetic energy. The gases have spread out, they're occupying a larger space, and so the entropy has increased. That's why we can't think of it as lowering the energy. We actually have increased entropy. For mixing, they mix because the energy is spreading out, is one way we can think of it. So this works for particles, for ions, like when we've got solutions mixing. It also works for the transfer of thermal energy. When you've got hot objects, they tend to lose their energy to cold objects that are around them. That's the energy spreading out or equilibrating over an area. Another factor at play when we're trying to dissolve things or mixing things together is intermolecular forces. There's 4 intermolecular forces that you should be familiar with, at least somewhat. They are dispersion forces. What things have dispersion forces? What class of chemicals has dispersion forces? Gases have dispersion forces, that's true. Anything else? Liquids also have dispersion forces. What types of gases and liquids? Everything. Everything has dispersion forces. If it has electrons, it has dispersion forces. So everything has dispersion forces. The dispersion forces are caused by, these are more complicated examples with heptane and pentane, but we've got electrons around each of our hydrogens here. They can randomly be on one side or the other. And if they're all randomly on one side, that de-shields the nucleus on the other side, and so we've got a slight positive charge. That positive charge can attract the electrons from a neighboring molecular atom just for a little brief period of time, and then maybe it'll be gone the next moment. And then it'll be back, and then it'll be back, and it'll be gone, and it'll be gone, and then it comes back. It fluctuates. It's instantaneous. It's not very strong. That's our dispersion force. We also have dipole-dipole forces. Dipole-dipole forces are stronger than dispersion forces. What kind of things have dipole-dipole forces? Maybe think about what's a dipole. Which pole do polar bears live at? Polar bears. It's either the North Pole or the South Pole. I can't remember off the top of my head, but we've got a North Pole, we've got a South Pole. That's how many poles? Two. Dipole. 2 poles. What else has 2 poles? Magnets. So dipole-dipole force are little magnet forces. Little forces between things that have dipoles. One of these days I'm going to figure out how to write without making mistakes. Today is not that day. So dipole, having 2 poles like a magnet, a positive and negative. Things that have a dipole, a permanent dipole, are polar molecules. Our third class of intermolecular forces, hydrogen bonding. As the name implies, this involves hydrogen. But wait, there's more. What else do we need? It has to be polar, that's true. There's a specific condition related to hydrogen. Dementia? Wrong kind of condition. That condition is hydrogen bonded to, who remembers? I heard fluorine.
Carbon.
Not carbon.
Oxygen.
Oxygen. Nitrogen. Those 3 things, because if we look at our periodic table, fluorine, oxygen, nitrogen are all very small. They're also very strongly electronegative. They can get really close to that hydrogen. When they get really close to each other and they're really strong, we could probably invoke Coulomb's law here. They're close to each other. They're strongly charged. They're going to create a bigger difference in electronegativity, or a different, not electronegativity, a bigger difference in total electron charge. Anyway, they're small and they're really strong. And that's the key point for hydrogen bonding. It's sort of like a super dipole force. And then our last force is the ion dipole force. So this is like our dipole force, but we've swapped out one of the dipoles for an ion, something that has a formal positive or negative charge. And this is sort of like Buzz Lightyear in the claw machine with all the little green men around him. They're all, save us. or whatever they do. Anyway, that's what comes to mind for me. So we've got all of these little dipoles stabilizing the positive or negative charge of our ion when they're in solution. Questions about that rough through intermolecular forces? Great. So hopefully you're a little freaked out about not remembering things there, if you weren't remembering things there. We're kind of just picking up with the assumption that you remember what happened in 1A, even though it's been a couple of weeks. So keep that in mind. Maybe a good idea to review some of your 1A if you've got time. Okay, so the way that intermolecular forces work, this is also sort of a review. Our intermolecular forces exist between a couple of sets of things. We've got interactions between our solvent, our majority component, or our liquid, and our solute, the thing that's dissolved in our solvent. So represented here, our solvent is these blue kind of oblong shapes, and our solute are the red round shapes. We've got interactions that can occur between our solvent and our solute, and that has a particular strength. We've also got solvent-solvent interactions, the solvent, how much it likes itself. And we've also got interactions between the solute particles, the things that we're trying to dissolve. You can sort of think of this like if you have people over, if you've got friends over, assuming you've got friends. If you've got two groups of friends, even rarer, one of those groups of friends might be the solvent-solvent, the other one might be the solute-solute. Sometimes friend groups don't get along well. You have to have enough interaction, enough commonality between the solvent and the solute for those groups to mesh well, for you to have fun at the movies or going out to play regular sized golf or mini golf or mega golf, whatever size golf you want to play. If they don't get along well, they're probably not going to stay together. That'll be the last time you go to a movie or play a size of golf. And that's because usually the solvent-solvent interactions, those are going to clump together, and the solute-solute interactions, those will clump together, and there's not enough interaction between those two groups, and so they'll separate. Those things are not going to dissolve. Usually that's because of the type of intermolecular forces that they have. The big phrase that we have for dissolving things in chemistry is like dissolve like. And you can substitute either of these likes for polar or nonpolar. Whereas for friend groups, maybe it's jocks and nerds. So for swapping out those likes, polar dissolves polar, nonpolar dissolves nonpolar because of the way that they are. And related to that, we've got the term miscible, which you maybe haven't thought of or heard of in a while. It's basically mixable, is one way to think about it. The formal definition, you can just combine them in any proportion. So you can have even proportions and they dissolve, they mix, they form a homogeneous mixture. You can have 1% of one and 99 of the other, 99 of the one, 1% of the other, any proportions, they'll mix together. That's what miscible is. Here's a table, kind of just describing the different conditions that you can have if your solvent-solute interactions are greater than the solvent-solvent and solute-solute interactions. So if this between the two groups force is bigger than the forces in the groups, probably going to mix. If they're equal, also probably going to mix. Things want to spread out, so they'll probably mix up. If your solvent-solute interactions are weaker, so if this little arrow is weaker, these groups will tend to stay towards themselves. It might still form a solution, might dissolve. but also maybe not. Just because if they're not very strongly attracted to each other, they're more likely to just keep to themselves. And then we'll stop after this practice slide. Determine whether each of these is soluble in hexane. So get those brain muscles working, see if you can remember what these things are. Slight correction for the recording. We're going to keep going for another half hour. All right, if you're stumped, we're thinking about intermolecular forces. That looks like forces. And like dissolves like. That's an and as opposed to a plus, and the little connection thing there is what makes it an and instead of a plus. Who remembers what hexane is? Who remembers what the ane ending means? It's all single bonds. That's one way to think of it. Somebody said 6 carbons. Hex. 6 carbon hydrocarbon. So C6H14. And it looks, probably, if we're talking about the straight chain variety, N-hexane, it would look something like this, where each of these bends is a carbon, and then we just attach 2 or 3 hydrogens, depending on how many they have room for. Who knows what kind of intermolecular forces hexane will have? Yeah, it has dispersion forces. How do we know it has dispersion forces? Everything has dispersion forces, that's right. We have electrons, we have dispersion forces. Anything else? Nope, it's just dispersion forces. We don't have a difference in electronegativity to have a polar molecule. Then we have to think about each of our options here. We've got water, ammonia, propane, and hydrogen chloride. The types of intermolecular forces that we have for each of these. Let's just talk about the strongest one. For water, we have hydrogen bonding. We've got our oxygen in the middle, the hydrogen's attached to it, meets our condition for hydrogen bonding. Ammonia also has hydrogen bonding. Fluorine, oxygen, or nitrogen bonded to hydrogen. This also has hydrogen bonding. What about propane? Any guesses what our strongest intermolecular force is for propane? It does not have dipole-dipole. You can think of it as just a smaller hexane. It's like if we chopped it in half, sort of. So this one also only has dispersion forces. We're just thinking about the intermolecular forces. We'll get to the like dissolves like. And then HCl, just hydrogen bonded to chlorine. What's our strongest intermolecular force there? Yeah, it's polar, so it's got dipole-dipole forces. So if we had to guess whether these compounds are soluble, thinking about like dissolves like, thinking about similar intermolecular forces, our hexane only has dispersion forces, very weak intermolecular forces. Which of these do we think is most likely to dissolve in hexane? Propane. Propane's most likely because it also has dispersion forces. Dispersion forces like dissolves like. So they're both nonpolar. Propane very likely to dissolve in hexane as long as it's not boiling and turned into a gas. What's our next candidate, if we had to guess? Yeah, hydrogen chloride probably is our next best candidate because it has dipole-dipole forces. That's a weaker force than our hydrogen bonding. It's a little bit more similar. It still probably won't dissolve, or at least not very well. So this is our next most likely to dissolve in hexane. Questions about that? Yeah.
How do you find out if it would be dissolvable, like for the hydrogen chloride?
You could try it. That would be one way. Or you probably look up the solubility of HCl in hexane. It's probably out there. Somebody's probably tested it and reported on it. Hexane's a very common solvent. All right, so that's stuff all kind of review from 3A, if you can believe it or not. New stuff, energetics. What's our energy doing when we are forming solutions? We can think of solution formation occurring as 3 steps. When we're mixing things together, our first step is we need to separate our solute. We need to make space. So our solute, our minority component, possibly a liquid, possibly a solid, could even be a gas. Regardless of what state it's in, it needs to separate out into its particles. It's not going to be dissolved if it's staying lumped together. And this will always be endothermic because we need to overcome our intermolecular forces. Even if they're the very weak dispersion forces, that's a little bit of force that we have to overcome to get them to not be stuck to each other. We have to put in a little bit of energy to get them to go away from each other. So our change in enthalpy of the solute is greater than 0. We're putting energy in, endothermic, the endo part meaning in, adding energy. So we're putting in some energy, we're separating out our minority component. We are also going to do the same thing for our solvent particles. Our solvent, our majority component, also needs to separate out. If we don't separate out our solvent, we won't have anywhere to put our solute. So this is sort of like if we were doing some Photoshop maybe. We're just going to separate all the particles out a little bit for both of the images. And then the next step, spoiler alert, we're just going to overlay them. We're going to move them into each other rather than combining them and trying to separate them later. This one's also endothermic. This time it's for the solvent, delta H solvent. Also endothermic because of intermolecular forces. And then finally, since we're talking about forming a solution, we're talking about mixing. So we're going to combine the two images together. So we combine our solute into the solvent, and this will be exothermic. They cozy in there, they find their little crooks and nannies, nooks and crannies. They settle in, we re-engage our intermolecular forces, and those intermolecular forces increase our stability, so they release energy. Sort of like when we form bonds, the act of forming bonds lowers the energy of the atoms, so it's exothermic. Another thing we learned in 1A. So our 3 steps. We're putting energy in to separate our solute. We're putting energy in to separate our solvent. Now that we've got space among both of those, we can add them together, re-engage our intermolecular forces, and we get an exothermic result. So the enthalpy of solution that's when we add together all 3 of those steps, separating out our solute, separating out our solvent, and mixing them together. Combine all of those, and that gives us the enthalpy of the solution. It'll be on the next slide, so I'm not going to write it here. Or maybe it's a few slides later. So the overall sign, positive or negative of our enthalpy of solution, depends on the individual enthalpy of solvent, enthalpy of solute, enthalpy of mixing. So when we're mixing things together, sometimes it's hot, sometimes it's not. Sometimes it absorbs heat. Here's a picture illustration of both of those conditions. Wow, that's a lot of stuff to look at. So where do we start? We're starting with our solvent aggregated, that's all put together, and our solute aggregated, all put together. Our first step, we're separating out the solute. So our little purple blobs here separate out. There's a little bit more space. It's not evenly mixed together, or it's not nice and uniform. we also separate out our solvent particles. So now we've got everything separated out. We had to put energy in, draw in our energy axis. We had to put energy in to separate these out, to overcome the intermolecular forces. We combine them together, and we get a lot of energy released because of the intermolecular forces re-engaging, like weak bonds forming. And in this particular process, our delta H of mixing was bigger than the energy it took to separate our solvent and our solute. So we overall released heat. Release a little bit of energy in that case. There's also the case where we separate out our solute, our little, in this case, orange, go Tigers, blobs. So we separate those out. We also separate out our solvent. Now that they're all separated out, we've made space. We combine them together, re-engage our intermolecular forces. In this case, the intermolecular forces weren't quite as strong. And so we actually had to put in some energy overall for that to happen. Usually when this is occurring, usually when we have an endothermic process rather than, or exothermic, it's coming from the solution. For an endothermic process, it just absorbs energy from the room or from the glass or the container that it's in. And so it'll feel cold because it's absorbed some of that extra thermal energy, that energy that's just around us. When we're doing this very fun, having a good time stuff with aqueous solutions, we can also combine our enthalpy of the solvent and enthalpy of mixing into the heat of hydration. Our heat of hydration is also an enthalpy change. It's that little h and the delta. And this is for 1 mole of gaseous solute ions dissolved, in this case for water. There's probably heat of hydration for other things, but maybe they call it something different. Our heat of hydration, always going to be largely negative. Lots of energy put out because our water is held together by dipole-dipole forces, hydrogen bonding forces, and the ion dipole force is just so much stronger that it's always going to be bigger. That's why it'll always be negative. So here's that math thing that I said that I wasn't going to write out because it was showing up later. Our change in enthalpy of the solution, or our heat of the solution, the solute, the solvent, separating both of those out, mixing them together. For ionic compounds, what makes something ionic? Metal and a nonmetal. So for things that have metals and nonmetals, things that form ions, ionic compounds, our enthalpy of our solute is equal to the opposite of our lattice energy. The lattice energy, something that was talked about in 1A. If our absolute value of our enthalpy of our solute is less than the heat of hydration, heat of hydration is always going to be exothermic. Delta H of the solute is always going to be endothermic, So we're going to have a positive, we're going to have a negative. If the heat of hydration's magnitude is bigger, if the number is bigger, then that means it's going to be exothermic. The opposite is also true. If the delta H of the solute is greater than the heat of hydration, then it will be endothermic. Questions? All right, solution equilibrium. Dissolving is also an equilibrium process. We've talked about previously evaporation and condensation being able to form a dynamic equilibrium. Dissolution, dissolving things, also is an equilibrium process. So if we take water and salt, we add a bunch of salt to our water. Initially, how much salt is there in our water? When we just have water, how much salt is there in our water? Before we add the salt, how much salt is there in our water? There's no salt, right? But we know that salt dissolves in water. So initially, there's going to be a very rapid rate of dissolution. We don't have any salt in our water, so it's going to go in really quick initially. If we just keep piling in the salt, or if we keep piling in the sugar, if we're doing sugar instead, eventually we'll get to a point where it really starts to slow down. You've maybe experienced this if you've tried to just heap tons and tons of salt, or hopefully not salt, but sugar into your water. As that concentration of our dissolved solute, our salt or our sugar, increases, the rate of recrystallization will also increase. In our little chemical equation here, the right arrow is dissolving, getting broken down into the ions, pulled apart, and our left arrow is recrystallization, or represents recrystallization, our solid or ionic compound reforming in the solution. And when we're at dynamic equilibrium, these rates are the same. So we've got things dissolving, we've got things recrystallizing. The rate that those happen are the same, and so we don't notice any change in our amounts. But initially, when there's no sodium or chloride, very fast rate of dissolving. If suddenly we had an excess of sodium and chloride ions compared to what we're supposed to have, for dynamic equilibrium, that would cause rapid recrystallization. And there are instances where that does occur. Here's an equilibrium diagram, or a diagram of what might happen when we're establishing equilibrium. Initially, we've got our little salt lick here in some water. No time has passed on our little clock. We've just mixed them together. There's no salt yet dissolved, so there's very rapid dissolution as we start. The water molecules are latching onto these positive and negatively charged ions, ripping them apart as fast as they possibly can. They're a kid on Christmas Day. or any other day where you open presents. And some time has passed. After a little bit more time, they're roughly equal. So there's a little bit of recrystallization occurring. There's a little bit of dissolution occurring. But the rates are equal, and so we don't notice a change. We don't observe a change in the concentrations when we've achieved that point. The concentrations, not equal. And we get some other terms that are related to our equilibrium. These are ones that we've talked about in 3A. Saturated solution is when the solute is in dynamic equilibrium, this dissolved solute, and the solid solute are in dynamic equilibrium. Caveat solid. Some solid solute may be present. If you're making simple syrup for lemonade or a fun drink, that would be represented by sugar at the bottom of your solution. In the lab, oftentimes a standard solution to have on hand if you do any organic stuff is saturated sodium chloride. You just dump as much salt as you want into a bunch of water. As long as there's salt floating around in the bottom, you know that it's saturated. There's no more that's going to go into solution. And so you can use it. You don't have to check the concentration. You know that you're using saturated sodium chloride. If you run out, you add more water. You make sure that you still have salt in the bottom. And that means you're good to go. It takes all the guesswork out of it. An unsaturated solution, however, contains less than the equilibrium amount of solute. No visible solid solute present. It's well dissolved in an unsaturated solution. This might also be the case for a saturated solution, but it's a much narrower band for a saturated solution because you'd have to be right at the limit. You can also get a supersaturated solution. Super meaning more than, like Superman's more than man. Supersaturated solution has more than the saturation amount. So this will often recrystallize sometimes very rapidly. Questions? One of the best ways to slow me down, asking questions. A question could include just, I'm confused, and then we'll work on figuring out what you're confused about. That's also a perfectly good excuse for coming to office hours. Just, Mr. K, I'm confused, and then we'll work together to figure out what you're confused about and try to resolve it. All right, look at this graph. The solubility of most solids, not all solids, but most solids, increases with increasing temperature. So on this graph, usually when you're explaining graphs, you have to explain what the axes are. You've seen this before, probably. Our x-axis, temperature. So as we're moving left to right, we're increasing temperature. Our y-axis, we've got solubility as grams solute in 100 grams H2O. As we're moving up the y-axis, we're increasing our solubility. So as we increase temperature, for most of these, solubility also increases. Sometimes it's linear, like with salt. Other times it's some other thing. And in the case of this thing, Ce2SO43, it's not increasing. It's actually decreasing with temperature. But for the most part, solubility increases with increasing temperature. You can dissolve more sugar, you can dissolve more salt, you can dissolve more of most things, if they're solids, as you increase the temperature. And that's important for recrystallization. So recrystallization, reforming crystals, reforming a solid. This is a technique to purify a solid. It's also a little bit finicky sometimes. So in order to do a recrystallization, you have to have a supersaturated solution. And below, we're describing how to create a supersaturated solution. Since solubility increases, we're preparing a saturated solution at an elevated temperature, and then usually allowing that to cool slowly. If you do it too quickly, if you cool it down too fast, you don't get a nice crystal formation. It collapses out, it crashes out a solution too quickly, and you don't get nice looking crystals. If you do it slowly enough, the solid forms these crystals, and that tends to reject impurities. You can make rock candy at home safely by recrystallizing table sugar. So what we're doing when we're doing a recrystallization, we're taking advantage of this temperature gradient. So let's say that we're doing it for potassium chlorate. Maybe we get our solution up to 90 degrees. So with that little green asterisk, right, our solubility is somewhere around 45 grams. Then we slowly cool the solution down. So we're moving to the left on this graph, and we can trace our curve. If we cool it down then to room temperature, our solubility is less than 10 grams. So all of that extra is going to come out at some point. If we cool it down slowly enough, that'll give it time to form those crystalline structures, form those nice lattices, and it will tend to exclude water and other things that are dissolved. And so you can end up with a purer substance as a result of recrystallization. Any final questions before we wrap up?